Picture this, January 4th, 2010, Dubai. A tower of glass and steel stands 2,717 feet tall, half a mile into the sky, crowned with the largest LED-illuminated facade ever created, the Burj Khalifa. A building so impossibly tall that American engineers initially calculated it would collapse under its own weight. They said the desert heat would crack the concrete before construction reached floor 50. They said pumping concrete over half a mile vertically defied the laws of physics. They were wrong. This is the story of how a Middle Eastern vision, Saudi investment, and revolutionary engineering created the world's tallest structure, a monument that rewrote every rule of construction and left the world's best engineers speechless. In 2004, Dubai faced an identity crisis. This small emirate sat on the edge of the Arabian desert with ambitious dreams, but a critical problem. How do you transform a desert trading port into a global icon that rivals New York, London, and Paris? The answer came from Saudi billionaire Prince Al-Walid bin Talal and Dubai's ruler Sheikh Mohammed bin Rashid Al Maktoum. Build the tallest structure humanity has ever created. The numbers seemed insane. 2,717 feet tall, nearly twice the height of the Empire State Building, 163 floors of mixed-use space, a construction budget of $1.5 billion. The building would require 330,000 cubic meters of concrete, 39,000 tons of steel rebar, and 142,000 square meters of glass. But here's what made American engineers nervous. Dubai's location presented perfect conditions for catastrophic failure. Summer temperatures exceeding 120 degrees Fahrenheit would cause concrete to cure too rapidly and crack. Sandstorms could sandblast workers and equipment. Wind forces at 2,700 feet would create lateral movements capable of making the top floors uninhabitable. One structural engineer from Chicago put it bluntly, we're not just pushing the envelope, we're throwing it away and starting from scratch. The journey began with a handshake in 2003 between Emaar Properties and Samsung C&T, backed heavily by Saudi capital. American architectural firm Skidmore, Owings, and Merrill received the commission, with Adrian Smith as lead architect. His sketches drew inspiration from the Hymenicalis flower, but those beautiful drawings revealed a terrifying engineering reality. Geologists discovered problematic soil conditions, layers of sand, weak cemented sandstone, and poorly cemented calciciltite. The ground simply couldn't support this weight without revolutionary foundation solutions. SOM assembled the largest engineering team ever for a single building. Over 380 specialized consultants from 12 countries. The planning phase consumed 18 months and generated over 200,000 engineering drawings. Computer simulations ran for 6 months, modeling everything from wind vortex shedding to thermal expansion. They discovered that without intervention, the tower's steel frame would expand 6 inches on the hottest days, enough to crack every window. But the real challenge was still ahead. And to build the world's tallest structure, they needed to reinvent construction materials. Engineers developed C80 concrete with a compressive strength of 12,000 pounds per square inch, twice as strong as typical high-rise concrete. The recipe included Portland cement from Pakistan, silica fume from Norway, and a revolutionary cooling admixture. But here's the innovation that shocked American engineers. Ice. Massive amounts of ice. Workers added ice to the concrete mix to keep temperatures below 95 degrees Fahrenheit during pouring. The project consumed 65 tons of ice daily, roughly equivalent to what 15,000 households use annually. The steel requirements were equally impressive: 39,000 tons of rebar, each piece cut to tolerances of less than 2 millimeters. The exterior featured 142,000 square meters of specialized glass panels with metallic oxide coatings that reflected 85% of solar radiation. The glass alone cost $217 million. Then came 27,000 hand-cut aluminum and stainless steel panels weighing over 4,000 tons total. Construction began on January 6, 2004, with a foundation that remains one of engineering's greatest achievements. Workers excavated 50,000 cubic meters of earth, reaching depths of 50 meters. The foundation consisted of a massive reinforced concrete raft supported by 194 board piles. Each pile extended 164 feet into bedrock, 5 feet in diameter, and reinforced with 67 tons of steel rebar. American drilling specialists worked in temperatures exceeding 110 degrees Fahrenheit. The foundation consumed 45,000 cubic meters of concrete. The largest continuous pour in history at the time, completed over 4 days without stopping. Vertical construction redefined what's possible. Using jump forming, crews advanced at one floor every 3 days. Instead of pumping concrete from ground level, they deployed the Putzmeister BSA 14,000, a German-manufactured beast weighing 430 tons that could generate pressures exceeding 5,500 psi. At peak construction, it pumped concrete to floor 156, nearly 2,000 feet above ground, a world record that still stands. Desert heat meant all concrete pours above floor 40 happened at night, when temperatures dropped below 100 degrees Fahrenheit. The construction site became a 24-hour operation with lighting rigs visible from space. The tower's Y-shaped design required perfect synchronization. Samsung C&T implemented GPS-based monitoring that tracked each floor's position to millimeter accuracy. When temperatures hit 125 degrees Fahrenheit, outdoor work ceased between 11 a.m. and 4 p.m. Workers operated in shifts with mandatory cooling breaks every 30 minutes. The project consumed 4 million gallons of drinking water annually just for worker hydration. The most spectacular innovation was the self-climbing formwork system, massive hydraulic platforms weighing 120 tons that literally climbed the building as it grew, providing workspace for up to 300 workers at deadly heights. Making a half-mile-tall building habitable required solving unprecedented problems. Wind engineering became critical. At 2,717 feet, wind speeds regularly exceed 100 miles per hour. The solution? A design tested in wind tunnels originally built for NASA spacecraft. The Y-shaped floor plan with setbacks creates a spiraling pattern that confuses the wind. As air hits the building, it creates vortices that cancel each other out through vortex shedding disruption. American structural engineers also installed a tuned mass damper system, making 1,000 micro-adjustments per hour, keeping sway under 6 feet. Water distribution presented another challenge. Pumping water half a mile vertically, standard pumps would explode under the required 800 plus psi pressure. Engineers created a cascade system with 46 pressurized tanks every 30 floors. Each tank feeds the next, reducing pressure requirements. The system also recycles gray water through filtration plants built into the tower, saving 15 million gallons annually. The elevator system includes 57 elevators, with the world's longest travel elevator at 1,654 feet, traveling at 33 feet per second. Otis developed specialized rope systems using ultra-strong steel cables that prevent stretching under enormous weight. Climate control features a double-skin facade, creating a thermal buffer zone, reducing heat gain by 40%. The air conditioning system pumps 946,000 liters of chilled water daily through 62 miles of piping. Despite being the world's tallest building, it uses 30% less energy per square foot than comparable high-rises, thanks to condensate recovery, producing 15 million gallons of water annually from air conditioning moisture. Before occupancy, the building underwent intense testing. American firms deployed ultrasonic equipment examining every weld and joint, discovering and fixing over 2,800 imperfections. Wind testing subjected scale models to simulated hurricanes in Canadian laboratories. Elevators underwent 20,000 test runs over 6 months. The building features 16 refuge floors with independent life support systems, each tested with simulated fire conditions. The Burj Khalifa fundamentally transformed the Middle East's relationship with architecture and engineering. Opening on January 4th, 2010, it shattered records. Tallest building, tallest freestanding structure, highest number of stories, highest occupied floor, and highest outdoor observation deck. Construction created 22,000 direct jobs and 90,000 indirect jobs. The surrounding downtown Dubai development generates over $5 billion annually. Property values within a mile increased 40% within 2 years. But the true impact transcends economics. The Burj Khalifa proved Middle Eastern engineering could surpass the West. American engineers who doubted the project now study its innovations. The concrete formula has been adopted worldwide. Wind mitigation strategies are taught in engineering schools globally. Over 17 million visitors have ascended to the observation decks. The tower sparked a renaissance in Middle Eastern engineering. UAE university enrollment in structural engineering increased 250%. The tower stands as a silver needle piercing the desert sky, visible from 95 kilometers away, announcing that human ambition has no ceiling. The Burj Khalifa is living proof that impossible is just an opinion waiting to be disproven. What began as a sketch became a half-mile monument to human ingenuity, a structure American engineers said couldn't be built, yet now dominates skylines and engineering textbooks worldwide.